I think that all that research that I had today basically led to this project. But the project wasn't started just to write a database. After all, who wants to write a database in his own sane mind? That's probably not a very good idea of how you should spend your couple next years. Because it's an interesting experience, but don't do it. My story is very simple. We just had a customer's project and that we were working on, and there were certain requirements. They are basically a non-stop pay-to-play SaaS system. So basically, they provide certain games that customers pay for to other basically distributors, and whenever end customers cannot pay, basically cannot register their entries to the game, the clients of the company that we're working with, they got really annoyed because they can't make money. That's terrible. So they needed to accept those payments at any cost, anytime. If the cluster is split in 5 pieces, they still need to do that, and they need to understand what was happening. So they had interesting conditions, like race conditions, for example. They needed to be able to pay out, but only once, because you don't want to collect your winnings twice. Well, you do want, they don't want you to do that. And refunds as well. You don't want to refund twice. You don't want to refund after the game is over. Obviously, you don't want, well, again, you do, they don't. And they obviously, since it's all related to money, they wanted to have some sort of audit trail. What was happening? Why? And if we lost money unexpectedly, why? And how do we fix that in the future? So those were problems that we were trying to attack. And we were obviously trying to use existing databases. We actually tried to use React, but we just felt that it's just not the right way for this particular application. Just doesn't feel right. Although the base is solid and it's great, it's seemingly what we need. But every time we run into those specific requirements by the customer, we ended up writing some sort of workarounds, and we didn't like that. So we decided, well, how about we take what's really important in React, which is React Core, which is the foundation of the platform, and play with it. So let me just give you a brief idea of what kind of database is this so that you have an understanding of what we're talking about. So in a traditional KV database, and by traditional I mean React and similar databases, and most of key value databases anyway. Let's assume you have a key that has a value of a certain list, let's say 1, 2, 3, 4. And let's have 2 clients, A and B. One of them will try to append the list. One of them will prepend the list with certain value. In this case, 5 and 0. So what's the result? Well, depending on the database you're using, either the latest write will win, or you'll have a conflict. And you'll have to figure out pretty much on your own what is the right behavior. So if the actual behavior that you want, that you have the whole list, well, you have to resolve the conflict, which means your application has to deal with that. It has to understand, by looking at the conflicts, it has to understand what the hell happened. How do I reconcile that? So what does Genomu do? Well, it has a well-defined behavior. In Genomu, that list will be 0, 1, 2, 3, 4, 5. And that's it. No conflicts, and everybody wins. So how do we do that? We do a variation of event sourcing idea. How many of you have heard about the idea of event sourcing? 2, 3, 4, about 4. OK, so well, the way I understand event sourcing is very simple. You basically describe events basically have a data representation for an event, and you send it to a certain endpoint, and it uses that to aggregate the final results of the computation. So, for example, if you think about a counter as an actor, for example, it receives a message increment, and that's an event. And it increments the value in the state, and that's the aggregation of that single event. If you have multiple increments, you have another aggregation. So in a nutshell, that's a very, very simple representation of event sourcing. So every command in Genomu is basically getting appended to the list of operations. So in this case, we have the starting list of 1, 2, 3, 4. And then, for example, depending on the order of events of clients A and B, we have either 1, 2, 3, 4, append 5 and prepend 0, or we have vice versa, prepend 0 and append 5. And the end result is, again, the list of 0, 1, 2, 3, 4, 5. But again, why? So let's dig deeper into motivation. So one of the important things that we had in that project specifically was that we were doing a lot of concurrent updates to different objects. So for example, we were doing a lot of counters. So how many bets are in the system? And for example, the list of things in certain containers. And obviously all those operations were happening concurrently. And when you're trying to update, for example, a counter, if your model is to read the value, then increment the counter and send it back in, then again you have a conflict, or the latest one wins and you don't have a correct counter. In our case, you actually save one round trip because you don't need to read anything. You just send an event out because you don't really care what's the value of the counter at that moment anyway. You say increment the counter, and the system takes care of ordering those events that get sent out of your application. So in the very end, it has the correct counter value. And the same thing with accumulators. You can just keep sending events like append to the list and saying, OK, this is a new element, this is new element, this is new element. And you never really need to know what is the content of that list. It might be a huge list, but as long as you're not transmitting it every time, you actually don't care what's the length of that list. And you might never actually transmit the whole list anyway. And I'll show why is that the case later on. Is that clear so far? Like any questions? Anything that is uncertain? No? Nothing? Okay, good. Another one, we haven't done much of that yet, but we're getting into this area these days. So the motivation is that, well, lots of web applications that are being written these days, they're using the term real-time web applications. And what they normally mean is that they continuously receive some streams of information, and they update the visual representation and the interaction with the user depending on that data. Problem is with many databases, yes, in many cases you can watch the changes to certain keys or certain structures. The problem is, how do you know what actually happened? So for example, you got the update that the key A have changed from value 1 to value 2. What actually happened? Do we know? In many cases, yes, we can sort of figure that out by knowing exactly how our application works and hope that it actually is being written well and we are not misinterpreting some facts. In our case, you can actually have a stream or a feed of operations that happen to the key you're watching. So you know what is the exact operation that happened to that key. So you don't have that ambiguity. You know, well, that's what happened. That's what it means. All right. So we can build those applications without having an extra logical layer to interpret stuff. We just know what's happening. And you can interact with the database in the same way, so you're keeping everything in one communication channel, which is interesting. And the third one is to enable highly available clusters in presence of net splits and in terms of data flow recovery. And what I mean by that, so let's assume that the cluster that we had for those games split up, but we still need to work with those gamers. And for example, they keep buying those bets, and we keep writing them down to the database, and we keep updating counters in those split parts of the cluster. But by the time we actually need to compute who wins, and who wins how much, and how many bets we have in the system, all that kind of stuff, we can wait until we have the recovery event in the cluster. But what we can do now, since we have the whole log of the updates for every key in the system and for every transaction effectively, we can recover the stream of events that happened and get the right aggregate values as well, and get the whole data set. And then when the cluster is healthy, we can actually do the draw and figure out what's the right jackpot value and all these kind of parameters. So that was probably the most important part of the initial project with that customer. So in a nutshell, what is this database? It's a key value database. It's an event sourcing engine. It's based on log merging, well, in case of failures. It has Redis-like operations, and I'll show you what I mean by that. And it's built on a Dynamo architecture. How many of you know what's a Dynamo architecture? Fair amount, I would say roughly half of you. So yeah, and we're using React Core technology from Basho to enable this. In a nutshell, what you can get from a Dynamo architecture is basically a highly available cluster that has multiple replicas of the data that you're writing, and it's rebalancing the data across the cluster when you grow the cluster or shrink the cluster. Obviously, there are more properties to it, but just as a very, very high level overview. For example, if you look at this, we're writing data. It's in presentation mode, so I can show this. But anyway, you can see the similar colors, so it's getting distributed across the ring. So next one, how can you actually use the database? Like, what's the way of interaction with the database? So your entry point is a message pack interface. How many of you know what message pack is? About a half. So message pack is actually an efficient binary serialization format. Think of JSON, but a binary that is actually cheap to encode, cheap to decode compared to JSON, because, well, JSON is a fairly complicated format to parse and encode. So it's really efficient, really tiny. And what we have on top of that, we have a very simple multiplexing protocol. So you can have multiple conversations with our server in the same TCP channel. So now we're getting to actual operations. So that's the cornerstone of the Genomu technology. So what that means is that unlike in React and some other databases, so instead of manipulating effectively binary data, when you read a piece of binary and you know what to do with it, and then you modify it and write it back to, say, React, we're doing something that is actually closer to, well, traditional SQL databases. In SQL, they know what the data type of your values are and what are the operations that you can do on them. For example, you can compare them, you can increment things, you know, they actually know what to do with that data. We're sort of the same way. We have a server-side library of those small operations that operate on message pack data types. In a way, like in Redis, those who are familiar with Redis probably know they have operations on strings, on binaries, on lists, on hashes, and tons of others. So it's a fairly rich library that you have at Redis, so that you basically take an operation and apply it to a certain value that is normally stored by a certain key. And we're the same way. So we have, say, numeric types, so you can do increments, decrements, and that kind of things. We have collections, such as lists, dicts, with support even operations like map, reduce, which is foldle, and others like filter, all, any, so standard functional programming language kind of operations on collections. We also have support for binaries, and we expect to have bit strings whenever the message pack guys will finalize their next standard that actually distinguishes, well, actually allows to define application-specific types. So we'll be able to define a bit string type, so you can start building things like bit planes for a bitmap kind of indexing for your own application. We have a very interesting thing called assertions. And assertion is a very interesting mechanism to fight race conditions and similar situations. So consider you're accepting certain records into your system, and you're also incrementing a counter so that you know how many elements of that kind you have in the system. Problem is, you actually will receive some duplicates once in a while. For whatever reason, the communication channels are not robust enough from some remote terminals, so you're getting resubmissions. How do you deal with that? So we have this special, well, almost special assertion operation, which means proceed only if this assertion passes. And if it does not, abort the transaction. So you assert that that element that you're trying, that key that you're going to write to is equal to a nil, which means, well, nobody have written to it yet. And if the assertion passes, your transaction goes forward, and then you write the actual object, and then you increment the counter. And the reason why this works is we have transactions that I will be talking about a little bit later, and you'll see what kind of interesting guarantees do they have that enable assertions, and I'll come back to that topic. And we have many more features in the pipeline, UTF-8 strings, so you can actually ask for the length of the UTF-8 string, and capitalize, uppercase, downcase, so do normal things that you can do with strings, except that you can do that remotely without sending data back and forth. Sets, possibly CRDT module as well, so for those who need very strict guarantees about ordering events. So many things. We're still trying to nail down the best set of the standard library. What should it be? And the other thing that I was mentioning before, for real-time web applications, we have this Watchers API, and it's very simple. You're basically subscribing to a key or a list of keys, and it delivers you messages that are effectively tuples of two elements. One is, well, what was the key affected in this transaction, and then the whole transaction object. And what that means, you can actually know all of the keys that have changed in that particular transaction, so you can know the scope of the change, which is oftentimes very important to know. So now that you know about operations, there are, at this moment at least, 4 commands. And they're very simple: get, set, apply, and commit. Let's just go through them. The first one is get. So basically what you do, you pick an operation that you want to apply to the value stored in the key, get the result, but actually do not change anything in the storage. So basically, the database remains intact. Just to give an example, consider that in that certain key, you're storing a binary, maybe even a huge binary, and all you want to know is its length. You don't want to get the binary, especially like from all the replicas, because it might be like 10 megabytes each, and that's going to take time. But you just want to know the length of that binary. So you pick the binary size operation, and you do get key binary size, and all you get is the size of the binary stored of that key. But it does not change anything in the database. It remains the same way it was. The opposite of that is set. It does apply the same kind of operation to a value. It returns you the result. So in that way, it's exactly like get. But it also saves that result into the database. Simple as that. Apply is just a variation of set, but instead of sending you the result back to you, it just sends an OK, because when you want to set the value, but you know that the result value is either of no interest to you or, say, too large to transmit, you just say apply, but I'm not interested in the result. Just save it and let it be there. And the most important after all these operations is commit. The reason why we have commit, because we actually have transactions in Genomu. So while you're doing commands like set, get, or apply, you're actually working within an isolation layer. So until you do a commit or discard this whole transaction, nobody will see the changes that you're making. They're completely isolated from you. Even though they are stored on the server, and eventually we might actually do something like persistent transactions that are like long-running transactions, but we don't know anything about that yet. Until you do a commit, they're completely unknown to anybody else. Once you commit, all those values get written to the database quorum by quorum, and then everybody else can access them. And the transactions that we have, they're not really ACID transactions, but they do provide enough of guarantees to be useful. So one is isolation, and the other one is causal consistency. So they're not consistent as in RDBMS kind of sense, but I'll show you an example in a few minutes that shows how you can build consistent views of data without basically sacrificing scalability and distribution of your data across the cluster. So I'll start with simple examples. Can you actually see it there? I hope so. So basically it just says set counter number increment commit. This is all you do to work with a simple counter. The next example is actually about causal dependencies or causal consistency. So yeah, I really want everybody to be able to see it. Is there anybody here that can see that? Okay.
The folks online have the live streamers, they have a very small.
Oh, okay. Well, I'll be vocalizing this then. So let's start with this simple scenario. So we have two actors in the system. One is Alice, and the other is Bob. So what Alice tries to work with here is a photo album of a kind that has a privacy setting. So when she supposedly creates the album, she sets the privacy to a value of public. So she defines that her album is public. And then she commits that transaction. Then she says, okay, so I'm appending a nice picture of myself to the list of photos in that album, and also commits it. And then she realizes, well, I actually want to upload some pictures, but I don't really feel like I want to share them with everybody. They're not so good. And she sets privacy of her photo album to private. And Bob, being an independent agent in the system, all he wants to do is to look at the pictures that Alice uploaded. So he goes to the database and asks for photos. So he says, get photos. And he gets photos, which is at this point is still just a nice picture. And notice here that we're getting a certain version back. So we know that's a version, let's call it version 1. So after this, and so this means that Alice has updated the privacy setting, and Bob got the pictures that were uploaded before. And what happens next? After this, Alice says, okay, so now I'm appending, I'm adding a private picture to the set of pictures, and I'm committing this. And now Bob, well, he's a little bit slow. Maybe he went, to grab a beer, and now he's actually ready to see the list. And he asks the system, okay, what's the privacy at the version 1? And it says, well, it's public. You can show it. And he shows, well, the list of pictures that does not include a private picture. But now he hits refresh. He wants to see more. And he goes through the same steps. So he requests the list of photos. And notice that we actually get a nice picture and a private picture. And then he asks, okay, what is the privacy at version 2 that we just got from that object? And it says it's private. So it knows that, but at this time, it cannot display the list of those pictures because it's private within this consistency view. And basically, the question here is what enables this kind of dependencies? So what we are using here is we are using another generalization of the vector clocks mechanism. How many of you are aware of vclogs? So about a half again. So vclog, the simplest way probably to explain it is it's a way to do partial ordering of events in a distributed system and to detect violations of causality. So, which event happened after which, basically. And ITC is a similar system, but it generalizes it to the point when you can have, when you don't need to have global unique identifiers for actors in the system. So it can grow and shrink as you need. So with this technology, we can actually have global versioning of every object, so we can compare the causality of any object in the system, not just one, which is different. So, and this is the reason why asking for a privacy setting for a specific version of a photo album actually works, because it's the global space for versioning. So what about availability? We just open sourced it a couple of days ago, about a week or so. It's available on GitHub, and as an alpha beta version, it already works. It has a fairly nice UI that you can use to monitor it, and in the next tab, it's called instances. You can actually assemble your cluster right from the web UI. So it's not tedious. It's actually fairly simple. And we do things like DNS SD. So for those who don't know what it is, it's a DNS Service Discovery. So if you launch a couple of instances in your local network, the system will see them, and you can just click Add and add them to the cluster without actually knowing where they are. Just you can find them in the list, because they will identify themselves using multicast. So another part of the talk is what it's implemented in. And how many of you came from the Elixir talk that was just, so again, roughly half. So as you know, basically for those who weren't at the Elixir talk, Elixir is a meta-programming-aware language on top of Erlang. So basically it takes Erlang and applies some interesting ideas from Lisp and related languages to it, and tries to create a more productive and extensible environment for Erlang developers, such as myself. And I just want to show a couple of things that really helped implementing Genomu and at least try to explain it why. So one of the things here is, since we're operating with message pack data types, we want to be able to work with message pack efficiently. The reason for this, when we operate with things, especially things like collections in our operations, so for example, here is the example how we extract the head of the list. So instead of constructing a list from message pack representations stored in the database and then actually getting the element out of it, and what we do, since we store a message pack, we basically work with binaries directly. We do not allocate Erlang terms at all. Well, just for a few exceptions that are actually not related to collections. But specifically for collections like binaries, lists, and dictionaries, we do not allocate anything in Erlang. We operate directly on binaries, which means we need to match on message pack data structures in binaries. But here are two examples. So if you look at the bottom one, you'll see that we would have to match on a specific part of the binary, saying it's in binary like 101, and then next 4 bits are the length of it, and then the rest is basically the rest of the list representation in message pack. But since we have macros in Elixir, the message pack library that we wrote, it actually contains macros for every data type in message pack. So instead of that line that, well, I can never remember those numbers, obviously, so I have to look them up, and I don't know what they mean, really. We have macros that generate exactly the same code, but we know how to write them. Because all I do, I write the head function definition, and I write message pack, fix array, and ask for the remainder of the binary so that I can work with that list specifically. But I know that it's a fixed size array, which means it's up to 16 elements. So I can match on specific types of message pack, and I don't need to care what the prefixes are, how long they are, how long the length is. So it's just being taken care of by the library that provides a couple of macros. And thanks to that, the operations on those especially complex data types like lists and binaries are very efficient in Genomu. So no new memory allocation really, and so we don't need to spend time on that either, which makes it fairly efficient. Other things that are worth mentioning, code generation. So for example, all those operations that you've saw, like the commands plus operations, they get encoded into an efficient binary representation as well. So for example, an operation called core identity, which is an operation that would just return the value stored in the key, it's encoded as 0, 0. So it's 2 bytes. The first one is for module. The second one is basically for the number, the identifier of the operation in that module. And the way we do dispatching, we actually compile time, because we are building the whole library in Elixir as well. Compile time, we produce enough function clauses in a central dispatching module that just matches on the beginning of the binary. So it knows all the combinations of module, operation, just matches to them and dispatches right away where it needs to go. So it's very fast again. So, and there's at this moment, we don't have many operations, maybe 50, 30, I don't know, something like that. So it's not that big of a deal, but when the library will grow, it will show a tremendous improvement because we don't need to do any ETS tables or anything. It's just compiled in, it's baked into the central dispatching module, and obviously it doesn't have any real bottlenecks because it can be executed by multiple cores at the same time without any problem. Another one, when we write modules, and you can look this up on GitHub, there's a link at the end of the presentation. We write documentation for those operations, for example, in the module. And during the compilation time, every time we compile the operations module, we extract the data about every operation. How many arguments does it declare? What is the documentation? What is the public name for it? And we actually generate both detailed documentation for it, so you can actually have like nice documentation. And we also produce JSON files for client libraries to know what kind of operations are available in this specific version of Genomu, so they can just basically use that to generate code themselves or just dispatch from the client libraries. But this is all part of the compilation process. It's not an extra step in the make file or anything like that. It's just baked in, again, into the compilation process. And if you're interested, at the end of the talk, I can show parts of the code that are actually very small, and they deliver all of that. And another thing worth mentioning is protocols. So how many of you have worked with Clojure or maybe Smalltalk? Not a lot. So basically, protocol is similar to interface in Java, I would say. Not exactly the same thing, but when you define how that thing should, like, to what kind of messages this thing should respond, and then you can dispatch to those particular implementations depending on the type that you're using. And in our case, it has been very useful for basically two things. One thing is storages, so we can implement a storage as a record and then define an implementation of a protocol. So we have implementations for, say, ETS, Bitcask, and other storages that operate through the same protocol. And the other one, since we do different kind of coordinations, we have commands like set, get, and apply, and we have a commit operation that operates on multiple quorums instead of a single quorum at a time. So that means it's a different kind of coordination. But the actual coordinator is only one module that we have there. But for specific logic for either operation coordination or transaction coordination, we have implementations defined for the important parts, like get the quorums, how we handle the responses from the backend. They're implemented through protocols. And if we'll ever need anything else that acts as a coordinator with respect to timeouts and everything like that, and coordinates actual quorums, but the logic is different, we just write another implementation of this protocol, and we're done. We don't need to change much in the system, which is really, really useful. And that's pretty much it. How are we with time?
12 minutes?
Left or 14 minutes left? Okay, so questions. I can show some stuff if anybody's interested.
So I have two questions.
Sure.
One, when you do a commit, is that when data is written to the log to get shared with the other members of the cluster, or does that happen before that?
It basically.
Could you repeat the question, please?
Oh, sure. The question is, so when you send a commit operation, is that when the log gets appended, or is that happening before that? Is that the question? So yes, this is the time when the actual log gets appended. Before this, it's basically what we call a staging area. So it just writes data by a version, and then the commit is basically linking that staged data into the log and updating aggressively cached data into the log itself. So at the top of the log, you always have the computed value, so that you don't have to recompute, the whole transaction log every time. So it's always cached at the top, so you know the values. But that's what happening at the commit time, yeah.
So that series of operations, does that get coordinated on all the members of the cluster? Like as you're negotiating quorum for each of these things, and the commit is when all of the members write to their log?
So yeah, the question is, I'm just trying to put it shortly. So the question is, does the commit operation try to negotiate with all members of
Or does it happen before
yeah
the commit?
so with all the members of the quorums included in that particular transaction, since you're working with multiple keys, right?
Right.
So the answer is basically what it does. It operates with multiple quorums. So it figures out quorums, sufficient number of quorums for the whole transaction to complete, and it sends out repackaged operation sets for every quorum. So we know these 3 operations belong to that quorum, and these 2 operations belong to this quorum. So we send out two quorums, and we wait until all quorums are finalized, and that's when the commit is considered successful.
So the other question I had, since you retain versions of data, how long do those versions hang around? Like, how do you manage the ever-growing population?
Well, it is growing, but actually the way ITCs grow, it's more like of this kind of stick. So it actually, the thing is, every time we create a transaction, we fork the tree of the clocks. But every time the transaction ends, it joins back. So in our experiments, we try to model the growth of this clock for a couple of years worth of operations, like with constant transactions. And I think it grew at about 29 bytes per version, which is still acceptable to us. Yeah, so I think it was 29 bytes in a binary representation. So we don't handle anything, like we don't have any specific handling for pruning that part of the clock yet. We might consider that in the future. It just hasn't been an issue so far. But that concern is always on the back of my head. So I'm trying to think maybe we'll have something like epochs in the system, so we can basically say at this point everything is fine, like the cluster is healthy, we can dump that part and start dumping it. But at this point we don't have that, but it's part of the plan, pretty much. Any other questions?
Yeah, one of your earliest examples was a prepend and an append, and how they could be combined together in either order to produce the same result.
Mm-hmm.
Of course, if you had chosen 2 appends, then the order would make a big difference as to the final list.
Mm-hmm.
So it wasn't clear to me how you deal with those kinds of orderings and where they really do interfere with each other.
Mm-hmm. So the question is, how do we deal with operations order for those operations where order actually matters? So when you want to append one thing and then another thing, and you don't want to append them in the other order. So at this moment, we don't have a good API for this, but the plan is very simple. Basically, for every transaction to be considered in a specific order, you need to basically join their clocks together and fork them again. So basically what we'll have is a synchronization primitive for transactions. So you know that these transactions at this part of the system, they need to be ordered. So basically every time before they do that, they need to do this short sync call and get the new clock, which will make every transaction in that part order it correctly. So you'll have the logical clock adjusted. So that's one way to deal with this. And the other way, we're thinking about adding a CRDT module to do the conflict resolution data type. I think that's what the acronym is for, to do certain operations like for growing sets and for counters that also might be interesting for that. But yeah, the basic idea is basically sync the clocks, and that will ensure the ordering when you need it. So yeah, it's clock synchronization. We don't have this as an API yet, but we're planning to add that pretty soon. Because yeah, we didn't really need it so far, but it was part of the original design that just didn't make in the code yet.
Could you elaborate a little bit more on what continues working and what stops working during cluster splits?
Mm-hmm.
And what you're able to reconcile automatically and what requires, some
Okay, so the question is what continues to work and what does not continue to work during the cluster split. Is that correct? So to answer this question, so basically, what is not going to work? What is not going to work when you're trying to write, to operate with certain keys, when specifying when you only need primary nodes, or primary V nodes in the React core terminology. So when all of the when those V nodes are not available to you, basically you're turning the knob right, and basically you're saying, well, I only want these kind of nodes, not a fallback kind of nodes, to respond to me, and then you'll have failures. But when you have a net split, in terms of Genomu itself, basically what it will do, it will keep collecting data into those logs. And when you have an event basically that is opposite to net split, so like net join, right? That's the time when it will start reconciling the keys that have participated in so basically it's a repair mode. So it will find out the most common denominator in the transaction. So when they're all equal, and from that point, it will basically start ordering them by ITC clocks and timestamps, depending on where those timestamps come from, and figure out the right ordering based on those two elements, and rebuild the value. So at the top of the log, you'll again have a new cached value that is representative of all operations applied to that key. Does that answer your question? Okay, cool. Any other questions? I think we're out of questions.
I guess I have